All right, welcome to Lecture 10 of Vector 101. I'm going to start by reminding you that we're in a bit of a weird schedule right now because row reduction ended up spanning 2 lectures. So even though we just covered fundamental spaces on Monday, we're actually going to talk for most of today about row reduction. But I think that's okay because null space is highly involved with row reduction, so it should be fine. All right. So here's our agenda. So we're going to start with row reduction, and then like right at the very end, we'll do null space computation. Maybe we might not actually compute the null space today. We might just look at the null space. Something else I should add is that today's lecture is probably going to go late. You can see down here at the bottom that I have 30 slides. We'll try not to go too late. Okay, and then reminders as usual. Doing the exercises is important. And actually, the exercises from last week, when I was doing them myself, I thought they were really cool. So yeah, they're worth doing. And then office hours, again, are always on Saturdays at 1 p.m. Pacific. Okay, instead of going into this, we're actually going to jump straight into Studio. Okay, so here we are in Roblox Studio, and I want to remind you that we're talking about systems of linear equations. This is what we talked about last week. And let me show you a system of linear equations. So here we have these 3 lines, and if I can show you the equations that define these lines, and these should look pretty familiar. If you've taken Algebra 1, you probably remember y equals mx plus b. This is the formula for a line. And so we have 3 of them, and we call this a system of linear equations. And then the solution to this system of linear equations is where all 3 of these lines intersect. So what you'll notice right now is that, well, there's one intersection here, and there's one intersection here and here. So there's 3 places where there's 2 lines intersecting, but there's no place where they all intersect at the same time. So this system actually has no solutions. Whereas a system like this, you'll see all 3 of the lines intersect at one spot, and so there's one solution. And then this system, all of the lines are on top of each other, and so there are infinitely many solutions. And then we can go up a dimension, so now we can look at a system of planes. So here's 3 planes, and again, I can show you the equations. A little difficult to see. Maybe we don't need this. Okay. Right. But in this system of equations, these planes, you can see that roughly around here is where they all intersect. Right. So these planes we can see have one solution. And then we can look at planes with no solution. So these planes here, you can see, well, the blue and the red intersect, and they intersect at a line. The blue and the green, they intersect at a line. But all 3 of them don't intersect in one spot, so there's no solution. And then lastly, here's a case where there are infinitely many solutions because all 3 of these planes, they intersect at a line. All right, so this is geometrically, when we talk about systems with linear equations, this is what we're looking at. We're looking at a system of lines, a system of planes, a system of hyperplanes in higher dimensions. And when we say we want to find the solution, we're looking at where they all intersect. So do we feel good about this? All right, thumbs up in the chat. So I'll switch back now to the lecture notes. Okay, so that was essentially what this slide was showing. So we'll just skip right past it, but yeah, system of linear equations. Right, and again, we also just saw this slide too. We saw cases where there was 0, 1, or infinitely many solutions, and so we can skip right past this as well. All right, so now we're going to talk about row reduction. last week we talked about row reduction, but it didn't go so well. That's what I'll say. So what I did is I went back into my linear algebra textbook and I consulted the pros because I had trouble presenting row reduction. And so we're just going to look at some examples from my textbook, basically. Yeah, but with each example we look at, we're going to learn something new about row reduction. And then at the end, we'll have a complete algorithm for it. So here's our first example. We have the system of linear equations, and you can see on the right side what it represents. So the solution is going to be where these two lines intersect. And can somebody remind me, like, what is the first thing we do when we start to solve a system of equations? Okay, okay. So one suggestion is stuff the equations in a matrix. We'll get to that. But that's not a bad answer. All right. So the first thing we'll do is we take this first row and we subtract a multiple of this first row from the second row. So that's what this is indicating here, is that we redefine the second row to be the second row minus 3 times the first row. And what this does is now we have lost a variable in the second row. So we've eliminated a variable, meaning we've simplified our system. But even though we've eliminated a variable, the solution has stayed the same. Okay, and this is explicitly what we did over here. So we took the second row right here, and we subtracted away 3 times the first row, and ended up with this. And by doing this, the solution stays the same, but now we've simplified it a little bit. And once we have this, well, now we can just solve for y and x, because we look at y and, well, y is now just 18 over 9, which is 2. And then we plug in 2 here, and we get that x is also 2, which lines up with our picture too. It looks like the solution should be about 2, 2, and that's right. So this is probably the simplest example of solving a linear system. So you should stop me now if you have questions, because it's going to get more complicated from here. Okay, all right, so I'll keep going. And what is our takeaway from this example? Well, our takeaway is that we can subtract away a multiple of one row from another to eliminate a variable. And this is like the thing that we're going to do again and again. All right, let's put that away for now, and we'll go on to our next example. So in our next example, we have a system of 3 equations, 3 variables. So this is, if you want to think about it, it's like a system of planes. And again, we'll do the same thing. So we're going to look at this number here, this 2, and we're going to subtract away twice this first row from the second. All right, and so by doing this, we've now eliminated this variable. So it's the same thing we just saw. We're now just doing it on a bigger system. All right, and then we'll do it again. Right. I meant to write that in myself, but right. So now we're going to look at the 2 again, and we're going to eliminate that 2 there. So now we have a 0 and a 0, and we're continuing to simplify our system of equations. And so I'm introducing some vocabulary here, which is that this 2 that did all the eliminating, we call that a pivot. All right, so we're using our trick, and well, we'll do it again. So here we look at this -1, and we add 3 times row 1 to row 3, and well, it's it's a little bit hard to see, but now we've also eliminated our number down there. what's the title of this presentation? This is lecture 10 of the course. All right, so we're continuing to use our trick, and now we're pretty much done. So we've eliminated this and this and this, and now we can see that W becomes 1, and then we can plug in 1 for here and solve for V to get 2, and then we can plug in both V and W to solve for U. Oh, I apologize. The topic today is on row reduction. Yeah. All right. So the process we followed is that we looked at our pivots and we eliminated everything beneath our pivots. And then at the end, when we got into this sort of like staircase sort of formation, then we do a process called back substitution. Right, and with back substitution, first we solve for W, and then we plug that in and solve for V, and then we plug in both V and W and solve for U. So that's back substitution. Right, so then our takeaway from this example, first of all, right, so we're going to apply this trick we have, this elimination trick. So we're going to start by applying it in the first pivot to eliminate the first column. And then we do it again. So we repeat this step on all of the remaining pivots. And then finally, we solve for the variables with back substitution. So this is the main row reduction algorithm. But we'll have to get into some edge cases next. All right, so let me know if you have any questions about this. Okay, the back substitution process. Oh, sorry, one sec. Okay, so back substitution is when we end up with a system like this, where we've used our pivots and we've eliminated below, and we used our pivot and we eliminated below. All right, so now we focus on this equation at the bottom. So we're left with this simple equation where we can now solve for W. So we solve for W by just dividing by -4, and we get W is 1. And then once we know W, we plug it in here, or right here, and this lets us solve for V. And now that we know W and V, we plug them in here, and we solve for U. So the comment is, so you solve for a variable and then substitute it back. Isn't that what was called the substitution method? The substitution method is like, it's like you try to do substitution, but on like the original system. And because you haven't row reduced yet, it's a enormous mess to do substitution. So first we row reduce, and then we can do back substitution, and it's a whole lot simpler. All right, so good. Now let's go on to our next example. Our systems keep getting larger. So with this example, we're just going to like verify that our process really works. So the first thing we'll do is, again, we'll look at this 2 and we'll eliminate down. So good. So now we got all zeros, and then we'll look at our next pivot, and again we'll eliminate down. And I'm going through this kind of quickly. Like, you don't have to mentally verify all of these equations. The point is that it works. Right, so we're continuing to use our elimination trick, and then finally we eliminate one last time. And again, we end up in this sort of staircase formation, like so. And we can see that we can quite easily solve for Z and then we back substitute. So substitute in for z to solve for w, plug in w and solve for v, plug in v and solve for u. So we eliminate and then we back substitute. And I should mention that this staircase formation, where everything below a pivot is 0, well, right, let me label these. So these are pivots. Everything below a pivot is 0. And when we have, right, when the system looks like this, we call this row echelon form. All right, so this seems to work really well. But now what we should think about is, when could this process break? When could this process break? Do we have any thoughts in the chat of when this process could break? When a row is all zeros. Yes, that is when it could break. And I think we'll see that right now. All right, so let's look at this example here. And again, we're going to use our elimination trick. So that's the first step. On here, I've actually eliminated 2 at the same time. So we took our pivot here, we eliminated down. Now we have zeros and zeros. And well, this row isn't quite all zeros, like Warp suggested, but there is a 0 in an important place, which is right here. So there's a 0 here. And when we look at this and we try to eliminate the row below, well, we can't. We are kind of stuck. Right, this is an issue. And thankfully, though, this is an issue that has a very simple solution, which is, yes, just as Borbis said in the chat, we just swap rows. And so what you'll notice is that right, I've swapped these 2 rows to get to these. So now the row with the 0 is below, and our pivot is a non-zero number again, which is good. That's what we want. So we have fixed our issue, and now we can continue. And well, our system is actually pretty much already solved. But that was an example of where you can run across an issue. And so our takeaway from this is we've added this part A onto step 2, which is if a pivot is ever 0, we swap it with a row below whose entry is non-zero. Meaning we looked at this and we saw that there was a 0 here. So we swapped it with the one below that has a non-zero entry. All right. What's another example where this could break? I'm not going to make you continue to watch me solve systems with linear equations. So this system right here we're looking at is like mid-solve. We're like on step 5 or something, all right? And so we come to this column. And we see, okay, well, there's no pivot here. It's 0. But what we just learned is that we can go and look for a pivot. So then we look at the row below. And shoot, the row below is also 0. So this is a catastrophe. Like, what do we do? This is horrible. And what it means is that our system has infinitely many solutions. Let me explain. So let's say, right, we run across this catastrophe, but we just keep going. Like, all right, so now we come down to here, and we eliminate down, and we end up with, we can solve for y, and then we can solve for x, and then we plug in y and x and y and x, and what are we left with? So we know y, we know x, but now we have 2 equations and 3 unknowns. So we don't know u, we don't know v, and we don't know w. And what this means is that, well, there are infinitely many solutions. Right, so like, we don't know u, v, or w, but let's say like we plugged in 5 for w, right? Now that we've chosen a value for w, then we can solve for u and v. And what if I chose a different value? Well, I could choose w to be 10, right? So now that I've chosen 10 for w, then I'm going to solve for u and v again. I'm going to get different values, but like the point is, anything we plug in for w will give a different solution for u and v. Meaning, w is what's called a free variable. We can choose it to be anything we want. All right, if there are no questions, I'll continue. Well, all right, what is our takeaway from this one? So here now we've added a part B to question 2, or to step 2, which is that if a pivot is ever 0 and there are no rows to swap with, well, we just skip it and go on to the next one. I mean, really what it is that it depends what you care about. Like if you're only after one solution and you come across this catastrophe and you find out that there's infinitely many solutions, well, then you can just stop there. And you know that there's more than one solution, so we don't care. But if your goal is to find all solutions, then you just keep going. All right, so this is our completed algorithm. There are no more edge cases, I claim. But maybe it's worth thinking about why there aren't any more. But this is what we do. So we made this observation that you can eliminate a row by subtracting a multiple of one row from another. And then we just repeatedly do this on all of the pivots. And there's these two edge cases, where if there's ever a 0, but there's a row below that's non-zero, we just swap it. And if there's no row to swap with, then we just keep going. And then at the end, we solve with back substitution. All right, how do we feel about this algorithm? Looks highly intuitive. That is good. All right, so we'll move on then. And we'll go back to an observation that Borg made earlier, which is that you can represent a linear system as matrices. So until now, we've just been looking at linear systems in this form, like with all the variables and so on. And we're thinking of them as lines and planes. And so we observed last week that this system is the same thing as this matrix equation. So there's a matrix A times this column vector X equals B. And it's the exact same thing as our system up here. And then what we also said is that, well, this X data is kind of redundant. Like we know that X1 is always in the first column, and X2 is always in the second column, and Xn is always in the nth column. So we said, well, it's kind of redundant, so let's just throw it out. And oftentimes we'll work with this form, which is called the augmented matrix. It's just kind of like a convenient notation, really. And my point in showing you this, that a linear system can be written as matrices, is because this is oftentimes, like if you take a linear algebra course, this is oftentimes how you're introduced to matrices. So we started with matrices as representing linear transformations, but this is actually, usually the order is switched. And so usually you would see this first. You would, like, matrices are motivated by linear systems usually. And what's good about this, representing the linear system as a matrix, is that you can actually represent the row operations as matrix operations. So let me show you. So if we wanted to scale a row, we would multiply our matrix by something that looks like this. So what this does is it's going to, whatever we multiply R by, it's going to scale the first row by C. And maybe let's verify it. At least just for the first one, we'll verify that this is true. So let's just multiply it by some vector, x, y, z. And for the first entry, we're going to get x times c plus y times 0 plus z times 0. And then for the second row, we'll get x times 0 plus y times 1 plus z times 0. And for the third row, we'll get x times 0 plus y times 0 plus z times 1. And the net result is, let's see, so this is 0, all of these go away, and we just get c, x, y, and z. So this matrix here ended up scaling the first row by c. And we can do this for our other row operations as well. So this matrix would swap the first row with the second row, and this matrix here would add a multiple it adds c times the first row to the third row. And I guess right, we do have an example down here. Yeah, maybe think about this example for a little on your own, but what you should notice is that this row and this row, so that the 2 goes down here, the 4 goes over to here, and so the row gets switched by multiplying by this matrix. And the really important fact that we get from all of this is that if we want to bring our matrix into either row echelon form or reduced row echelon form, all we do is we take A, and then we multiply by these matrices, by this series of matrices. We end up in our reduced form. So that's just something, I don't think we'll talk about this again, but I think it's cool. And maybe I'll just throw a bit of vocab at you. These are called elementary operations. All right, so traditionally, this is how you are introduced to matrices. But all of that was just a little bit of a detour. Now let's get back to our linear system. So we've figured out our algorithm to bring it into row echelon form. And now we need to look at the results. How many solutions do we have? So a case where we have 0 solutions is when we end up with something like this. And what you'll notice about this row, oh, by the way, these stars, they just stand for any number. But what you'll notice is that if you convert this last row back into the equation form, what we get is like 0x plus 0y plus 0z plus 0w is 12. And so what we get is this equation says that 0 equals 12, which is nonsense. So there is no solution to this linear system. And then a case where we end up with one solution is when every column has a pivot. So there's a pivot here and a pivot here and a pivot here. And then we can use our trusty back substitution to solve for the singular solution. And then lastly, as we saw, to get infinitely many solutions, what happens is some of the columns don't have pivots. So this column doesn't have a pivot, These are called free variables. And like to be clear, that the pivot is like you start on the first row and then you walk to the right, and it's the first number you hit. So this is the first number we hit, and that's the first number we hit. So that's why these guys are not pivots. All right, so we're going to get into the code soon. Before we get into the code, I have to hit you with a few more bits of information. Sorry if all of this is a lot all at once. So when we actually go to implement our row reduction, we're going to do something. We're going to add a little step to this process. So instead of doing back substitution, what we're going to do is we're going to bring our matrix to what's called reduced row echelon form. And we talked about this on Monday, but I'll remind you what it is. So reduced row echelon form is something like this down here. We see our staircase pattern, so we know it's in row echelon form. But what makes it reduced row echelon form is that each pivot has zeros above and below. So this pivot here, it's zeros above and below. This pivot here has zeros, this pivot has zeros. And what's more is that each of the pivots is 1. And to do this, you finish your row reduction, and then you can just rescale each row so that the pivot is 1. We call this reduced row echelon form. And the way we get to reduced row echelon form is that, well, first we do our elimination, which we know how to do pretty well. And then you basically just do the same process, but going up. So then you eliminate up, meaning you would look at this pivot. So we get to the end, we look at this pivot, and then we eliminate upward. And we look at this pivot and we eliminate upward, and we look at this pivot, we eliminate upward. And this is how we get into reduced row echelon form. And like, if you want to solve a linear system, you don't have to do this, but it's nice to have for other algorithms, such as computing the null space. So that's why we're going to do it this way. And then I think this is our last implementation detail. Yeah. So this one is a strictly like computational detail, which is each time we eliminate, we're doing a subtraction and a division. And the issue with this is that, or what do I mean? So like through our process, we often do something like this where we'll eliminate a variable in row 2 by subtracting something from row 1, or we, how do I say this? Let me just write up a system here. All right, so if we want to eliminate row 2, what we do is we redefine it so that we subtract away, is it b over a? I think we subtract away b over a of row 1. And what happens is if a is a really small number, we actually introduce a lot of numerical error. Is that right? Or is it b? No, I think this is right. Yeah. So if this is like, if b is like 800 and we divide it by some really small number, this sort of operation is prone to numerical error. And what we want to do instead is choose the pivot row to have the largest number in the pivot. Right, so like if A is really small and B is really large, then we're going to swap them. And we're going to eliminate using this row instead. And it just reduces numerical error. I don't know if, depending on time, we might do this today. We might not. If we don't, it's good to know, and I would encourage you to also include this in your own implementation. Okay, so this is called partial pivoting. Before we get into the code, do we have any questions about row reduction, how we interpret the solution to row reduction, any of these extra implementation details I've mentioned? Okay, in that case, we'll get into the code. And if you're in the camp of like, I'm so confused that I don't know what to ask, let me know too. And you can always also ask a question in the chat, or you can combine office hours. But that is okay to feel. Okay, here we are in Studio, and before we get into the row reduction, I wanted to show you one more visual. Well, it's not pre-prepared, but so let me show you, let me pull up the solution. Okay, I just want to explain how you can think about row reduction geometrically. So we know that when we have this system of planes, we can just kind of look at them, we see, okay, well, they all intersect right there. So there's one solution. And what happens when we do row reduction is you're gonna see these planes rotate. Like when we do row reduction, we are literally changing the planes. So you're gonna see them like rotate and move, but what we're not changing is the set of solutions. So throughout the row reduction process, the planes are gonna shift, but they're still always going to intersect at that one point. So they're gonna like rotate around that one point. So the planes change, but the solution does not. So I wish I could have shown you an animation of that. Didn't have time, unfortunately, but that's how you can think about row reduction geometrically. Okay, so let's get into the code. And what you'll notice is new this week is that I've created this linear algebra module. And the only point of this module is to require the ones inside of it. And the point here is that we are starting to build up this code base, and the point is that we're like creating our own library. By the end of these 10 weeks, our goal for you is to have your own linear algebra library that you can use in your projects. And all I'm doing is just emphasizing that we're building a library. And I guess the only thing that's missing from here is I actually forgot to put in the subspace object. So we actually have five modules already. Okay, I'm going to delete that, and we're going to create a new row reduce. We actually did get row reduce started last week. I don't think I actually have that on my computer right now, so we'll have to restart. But maybe that's not the worst thing. Okay, so, well, let's just do some of the boilerplate. And we take in a matrix, we'll return our reduce function, and we're also going to need our matrix class. All right, and then something else I had done last week was a little contentious, I guess, was the first thing I did is I copied the matrix input, because as we do our row reduction, we're going to be modifying the matrix. We don't want to be, we want to be respectful of the data that we're given. So we're not going to modify the original matrix. We're just going to copy it and then modify the copy. All right. And then the next thing we're going to want to do is we're going to keep track of our pivot. And remember, we can come across situations where our pivot is 0 and everything below it is 0. So our pivot just shifts to the right. So there's cases where our pivot will shift down and to the right, and there's cases where it will shift only to the right. So we need to keep track of the row and column of our pivot separately. So our pivot will begin at 1, 1, and we'll adjust it as we go. The way we're going to do this is we're going to perform some code as long as our pivot is within bounds of our matrix. All right, and now let's just hit the highlights first before coding anything. Like, what are we going to do? So the first thing in our algorithm is that we eliminate downward. So we're going to look at the pivot, and then we're going to eliminate everything below it. Well, there's something to do before that. So before, we have to make sure that our pivot is non-zero. So we're actually going to have to swap rows if needed. That is, if the pivot is 0. And then even before that, we could actually do partial pivoting. Remember, partial pivoting is when you choose the row whose entry in the column is largest, just to reduce numerical error, but maybe we won't do that for today. But you could do partial pivoting, and then actually partial pivoting would kind of consume the next step. You don't need to do the next step if you do partial pivoting. Right, and then I guess there's one other case we need to care about, which is if the pivot is 0, then we just move on. So if the pivot is 0, there's nothing to eliminate. And then the last step, I kind of went over this very briefly, but because our row reduce function brings our matrix to reduced row echelon form, remember all of the pivots in reduced row echelon form are 1. At the very end, we're going to normalize the pivot row. And what I mean is we make the pivot equal to 1. We just scale it until the pivot is 1. So this is the process, and well, this first step is kind of optional, and I don't think we'll do it today. Right, so our algorithm is like we look at the pivot. If it's 0, we look for a row to swap it with. If there's no row to swap it with, we just move on. So I guess this isn't precisely correct. So if the pivot is 0 and there's no row to swap with, then we move on. But if we don't have to move on, then we're going to eliminate the rows below it and then finally normalize. So this is the process. Now we can start to fill out each of these things. And how should we do this? So first, let's get the pivot. So the pivot is going to be we're going to index the matrix by the pivot row index and then by the pivot column index. And if the pivot is 0, then we need to look for another pivot to swap it with. And the way we're going to do this okay, so this is a little bit strange because in my code I've coded it using partial pivoting, and now I'm trying to not do partial pivoting on the fly. I guess what we'll do is we're going to look at all the rows beneath it and try to swap it with something, meaning we're going to loop through starting at the next row index all the way until the end, we're going to look for a row to swap it with. So if the ith row and the pivot column index is non-zero, then we can do this swapping. This means we found a row to swap with. And how do we do this in Lua? I think it should work if we just do, we swap this row with the ith row. Let's see. So we want to swap the ith row with the pivot row. That should work. Okay, so that addresses the case where, and let's also break at the end. So we found a pivot, which is bad, or no, our pivot is 0, but we found a row to swap it with, which is good. Now let's think about the case where there's no other rows to swap with. So we need some like success criteria. So if we were successful in finding a row to swap with, then that's good. But if we weren't successful, then all we do is we increment our pivot, our column index, and we move on. And so we'll just continue on to the next step. So this addresses our edge cases. And let's see. So we did this. So we swapped rows if needed. And if the pivot is 0, then we just move on. So let me stick this up here. All right, we've handled our edge cases, and now let's do the elimination step. Okay. Something I've done. Okay, so I was explaining the implementation details. What I said is that we're going to bring it to reduced row echelon form, which means that you first eliminate down, and then you eliminate up. And what's pretty neat is that you can actually do these at the same time. We can eliminate all the rows below and all the rows above a pivot at the same time. And here's how we're going to do it. So we're going to loop through all of our rows. And then we're going to, well, we're not going to eliminate the pivot row. So let's just make sure that I is not the pivot row. Then we're going to eliminate this row, and we're gonna jettison this out to another function. So we're going to eliminate, using the pivot row, we'll eliminate the ith row, and the pivot column. All right, so now we'll go define our eliminate function. I'll do that up here. And by the way, we're nearly at time. I think I said at the beginning, I don't recall if it was on recording, we're actually going to go a little bit over time. I think in this audience, I don't think this particular audience will mind more linear algebra, but I'm not going to try to go past the hour. So here's our eliminate row function. So we're going to eliminate using the pivot row. And then what I've called it is the victim row. This is the row that we're eliminating. And then the column that we're eliminating in, it is this index. So let's again, we'll get the pivot from the pivot row. And then we'll also get the victim index. So it's okay, I'll keep going. So like this is the number that we want to eliminate. But if the victim is already 0, then there's nothing to eliminate. And so we'll just return. So here's an early exit where there's nothing to eliminate. Neptune, I don't know what to make of that comment. Yeah, I wish I could have come up with a better name, but this is what I went with. So then the scale factor we're going to use to eliminate, so we're going to divide the victim by the pivot. And so remember, like, we're not implementing partial pivoting today, but the point of partial pivoting is so that when we do this division, pivot is not some really small number that builds our numerical error. And now we can subtract the pivot row from the victim row. So then the element in the kth column, we're going to subtract away the scale factor times the element in the kth column from the pivot row. And then I've done one last thing here, which is, like, the point is for the victim to become 0, but there's a tendency for it to become like some really small number that's not exactly 0. This is just a floating point thing. So if our number is actually, like, if this thing that we just tried to eliminate is like almost 0, well, then we'll just set it to 0. Like, we know what we were intending to do. All right, so this is how we're going to eliminate a row. We get a pivot, we get the scale factor of the victim element with the pivot, and then we subtract away the pivot row from the victim row. And we still have an issue. Oh, what is pivot row? I think pivot row is supposed to be matrix pivot row index. That's right. Yeah, I guess I should have defined this up here. So pivot row is going to be matrix pivot row index, and then the pivot is going to be the pivot row index, pivot row. There we go. Okay. So we're very nearly there. All we have to do now is normalize the row. By normalize, I mean we're going to scale each row so that the pivot is 1. So we're going to loop through each element in the pivot row, and we're just going to divide it out by the pivot, which scales the pivot to 1. And then at the very end, we're going to increment our pivot. So we're going to move it on to the next row, and we'll move it on to the next column. And then lastly, we just return our matrix. Okay, so that was a lot. That was a lot in a very little amount of time. My homework to you is basically going to be do this yourself, because it's, I think, basically impossible to take in all of this just from watching. Well, okay, before we finish, we should make sure that it, like, works, or roughly works. Even if we don't have partial pivoting, it should roughly work. All right, let me check back on my notes so that we can test it on a system whose solution we know. Oh, actually, I didn't, in my notes, I didn't do any reduced row echelon form. Okay, here's what we'll do. So we're going to call row reduce. So first, let's make a new matrix. And it's going to be 2, -1, 0, 0, -1, 2, -1, 0. Sorry, I'm just reading verbatim off my notes. Okay, and then we'll row reduce. We'll row reduce our matrix. And let's print out the matrix, and we'll print out the reduced form, and hopefully we see this in reduced row echelon form. All right, always a good sign when you start with an error. assertion failed. Ah, I gave it a bad input. These matrices should be in brackets. Okay. Oh, that looks a little wonky. Darn, so my two-string function doesn't work. Okay, so this is the system that we just put in, and the system we get out is the identity matrix, and you'll notice that the identity matrix is in reduced row echelon form. So it looks like, hopefully, we did it correct. And there's row reduction. Where does the augmented part of the matrix come in? Yeah, so that's true. We didn't actually augment it with any vector. Basically what you do is, so you have some 3x3 matrix, right? And you want to augment it with with another column on the right side. All you do is you create a 3x4 matrix, and you chuck in that augmented row into the last column, and then you do your row reduction. So you just make a bigger matrix, basically. Nope. I mean, it won't confuse the matrix here, or it won't confuse the algorithm, because you're still giving it a matrix. Yeah, I guess is there a reason why that would be a bad idea? I don't think so. Basically, you're never going to do. All right, look at my screen here. Let's say that our original matrix was only the first 3 columns, and then we augmented it with this last column. You should, right? So if this column were augmented, and you get to something like this, what it means is that we had a lie. We're saying that 0 equals 1. So you'll never get to a step where you're eliminating using only the augmented portion. Well, or maybe, I think you could, actually. I don't think it matters, though. I think there's not an issue here. All right, oh no, okay, there's only 2 minutes left. I had promised cool pictures, and you're gonna get some cool pictures. Let me switch back to my notes. Yeah, I'll answer the question in the chat, Shirka Day, once the recording is over. All right, so the last thing, I said that we were going to get to some of the content from Monday. Now we're getting to that content, which is the null space. So on Monday, we talked about the null space. Let me actually erase this. I think it'll be better if I just draw it live for you. So the null space of a matrix is the set of all vectors such that this system is true. So basically what you're doing is you're taking A and you're augmenting it with 0 and solving for the solution. So you're basically doing the exact same thing we just did, but you augment it with 0. So it seems simple enough, but we should think about what this means. Let me draw a diagram for you. All right, so our matrix A is, well, we can think about it as like a linear transformation, and it eats vectors from Rn and spits out vectors in Rm. And right? So we map these vectors under A. And first we can, like, so let's draw out the space where A maps to. So A is going to map every vector in Rn to some vector in Rm. And it won't necessarily be all of Rm. Like we might map to, say, a plane inside of R3. So we might not necessarily map to Rm. We could, we might not. We call this the image of A, but like that's not very important. What we care about is the kernel, or the null space. So one of the things that we map to is certainly going to be the zero vector. The zero vector always maps to the zero vector. And the null space is everything that gets mapped to 0. Oh, that was horrible. So everything here and the null space of A gets mapped to 0. So like all of these x's that satisfy this equation, what this is saying is that A maps x to 0. All right, and now I'm like super over time, so feel free to head out. I guess I'll just keep going. I want to get to these diagrams, so I guess I got quite ambitious today. Yeah, the zero vector always maps to the zero vector. Sorry, let me finish my train of thought. Let's finish lecture today, and then I'll get to questions. So look, now we're gonna have to jump back into studio. All right, so we're done with coding. The last thing I want to show you is some cool pictures. So with this demo, and remember, all this code is up on GitHub, so you can play with this yourself. With this demo, we can look at the row space, column space, null space, all these fundamental spaces. We only mentioned the null space today. We mentioned the other ones on Monday, but we can look at all of them. So we saw this diagram, something like this, on week 2. And what we said was, these vectors here, these green, these red, and these blue, these are like the standard basis vectors. And, well, not exactly. So what this is showing is it's showing a linear transformation, and it's showing how the linear transformation transforms our space. So what the green is showing is that the vector, the unit vector pointing up gets mapped to the green vector, and the unit vector pointing this way gets mapped to the blue vector, right? And so like it skews our space. These green, these red, and these blue, these are the columns of our matrix. Columns tell us where the standard basis vectors go. And so what you're looking at here, this weird skewed blob thing, this is the column space. The column space is all of the linear combinations of the columns. So you can add up green, you can add up blue, you can add up red in different amounts to get everything in here, and like really, well, really what you should be seeing, like this column space is it should fill all of R3. I can't show you that, but let me show you a column space that doesn't fill all of R3. So like here's my linear transformation, and what I'm going to do is I'm just going to crush this. Actually, let me, oh, I screwed it up again. Let me turn these on. One stud. Let me crush this. Okay, and so now our column space is only spanned by 2 vectors because we crushed the other one, and so our column space is just a plane. All right. Anyway, let's look at the null space now. What does the null space look like? and it'll, well, yeah, we'll start with just the null space. So let's think about, like, the null space is all of the vectors that get sent to 0. And well, right now, the only thing that's getting sent to 0 is the 0 vector. Like, the 0 vector always maps to 0. Borb asked a question, why is this true? I'll answer that after lecture. But now we can map more things to 0. So in a different increment. Oh goodness. Just go to 0. Oh, you're kidding me. I think there's like, I think we're suffering from floating point. Wait a second. Something is not right here. Yeah, okay, so what you should be seeing is a blue line. That you should be seeing a blue line that's horizontal to my mouse, because all of those vectors get crushed to 0. Oh, this is so unfortunate. This worked just last night. Does the left null space work? Well, the left null space works. The left null space, so what's cool about the left null space is that it's always perpendicular to the column space. So like the column space tells us, after we do a linear transformation, what are all of the vectors that we can achieve. And then the left null space tells us like the vectors we can't achieve. So like we're confined to the plane and we can't walk in this pink direction at all. Like that's the left null space. But gosh, I really wish I could show you the null space. What have I done? Oh, I don't know. All right. Well, if I fix this, I'll let you guys know after lecture. Yeah. All right. Something's broken. Well, I hope at least the column space and null space, left null space visuals were cool. Like, so something like what you notice now is that because our column space is just this one vector, the column space is this line, and the all of the directions we can't walk in, the left null space is this plane. So that's what that's showing. So I'll let you guys know if I get the null space demo working. So sorry about the long lecture. Thank you all for sticking around, and I'll hang around for questions.